Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Morning. I'd like to welcome you all to our lecture this morning. This is an MSR lecture transported over here to product land. So be nice to our person, to Ramsey, or viciously brutal, I don't care. It's my pleasure to introduce Ramsey Arpachi-Dussault. Ramsey is graduated in 99, actually December of 99. It was like December 31st.
No, not quite.
Oh, just before the Y2K rollover, I think was what he was after. One of David Patterson's students at UC Berkeley. He's now a professor at the University of Wisconsin. He and his wife, Andrea, lead the team there, and the systems storage team. And they have produced just a string of fantastic graduate students and a string of fantastic papers. In fact, we had one of his graduate students here this spring, and Neil was impressed enough that Neil said, hey, we should bring it, instead of having the graduate students, we should have the professor come. So that's why we brought Ramsey in, and hope you all enjoy his talk.
I guess, can you hear me? Is that good? Okay, thank you for having me. I guess I wanted to clarify at the beginning, I'm not sure it's an upgrade to go from the graduate student to the professor, so, but I'll do my best. So in any case, thanks for the nice introduction. My name is Ramsey Arpachi-Dussault, and I'll be talking today about some work we've been doing really on file systems and reliability, which is what we've been thinking about more or less for about past 4 or 5 years. And not being above pandering to the crowd, my more accurate title is this. I figured I might get some applause, and maybe it's the last time I will. You can imagine when I give this talk to the Linux developers, I give a slightly different title. In any case, this talk is I'm going to warn you, I guess, ahead of time. The talk is a pretty broad overview, and because I wanted to touch on as many different things that we've done instead of going to any one thing which you may or may not find interesting. So if you have questions, which I'm sure you will, and I'm sure I don't need to tell you this, please interrupt me, and we can go into more detail if need be, and I'm also around during the day if you want to find more time to talk offline. And so in some sense, I guess I'm apologizing ahead of time because any talk that's broad tends to be unsatisfying about any one particular thing, and so that is by its very nature. Please do interrupt with questions if you find anything interesting or if you want more detail. Okay, so in any case, what I'm going to tell you about the very first thing is I'll tell you about how this worked. How did we get interested in reliability of file systems? And it really started in this very simple thing that we were doing, which didn't really relate too much to file system reliability. We were building a RAID system that was trying to be smart about which blocks it made replicas of. And so, for example, it would try to learn things like, oh, this is an inode of the file system, or these are directories. Maybe this is the root directory of a file system. Maybe I should make more copies of that. So it was this RAID system we were building. And underneath, of course, on top of that sat a file system. And we were dealing with Linux file systems like ext2 even at that time, very simple Linux file system. And here's on the right, over here you see a very, it's okay if I walk around and stuff? Is that cool? You can see here a very simple file system. Maybe it has a super block. Maybe it has some blocks that have inodes in them. And then maybe it has some data blocks. And what we noticed when we were injecting some failures underneath this file system, and we noticed some very kind of interesting behaviors. So let me do this little animation. Like, let's say we're trying to, somebody was trying to read a data block from the file system. So that read request would go down to the disk, and then let's say we injected a failure in there, and so then the disk the layer that we were injecting failures would say, oh no, that you tried to do that, and it was a failure. Then what would happen is, let's say that application so the application would actually get a literal failure, and maybe the application was smart, or maybe it was trying to do something interesting, so it would come back, maybe try to read that same block again, and the next time, what would happen is, let's say it would succeed. Yeah, I know, I was bored last night, and I started playing around with the animation. So my apology for all the completely unnecessary animations. There's only a few in the talk. but unfortunately I started with one there. So anyway, let's say this time it succeeded, and then the file system would happily try again and return success, and the application would be happy. What we then did is we failed one of these inode blocks over here. So let's say you're statting a file, you're going to access an inode, and a read goes down to the disk. The same failure would occur over here. But the different behavior that the file system had, and as I said, this was Linux ext2 some years ago that we were looking at, is no matter what you did, it would never try to use that block again, that inode block. And this is kind of a minor thing, but as a researcher, I think sometimes these minor things stand out. And for me, it was kind of unusual. I'd been teaching people about file systems for some years at that point, and I'd never really heard of what is the file system's policy for dealing with faults. And that seemed like kind of an interesting thing, and I'd never really heard people talk about it. And I certainly didn't know for, say, the given Linux file systems or NTFS, what their policies were in terms of how they handle different kinds of faults when faults do arise. So that was just something that came up. Then another thing happened shortly after that, which was we were visiting EMC, big storage vendor. And interestingly, they were building a cluster storage system, and on each node was basically a PC running Linux and running a particular different Linux file system called RiserFS. And we heard those engineers complaining about some bizarre behavior of RiserFS when a corruption happened. So like one block would get corrupt, and then RiserFS would go crazy and rebuild everything that it could from scratch, and the system would go offline for many minutes while this happened. And again, the observation was there was some kind of hidden policy going on. I didn't know, when people talk about these file systems, they didn't say, oh, this is the file system that acts this way when a failure occurs or that way. There were these hidden policies. And so it led us to this very general question, which started as really an area of ignorance, is how do file systems react to disk failures? And that's how we really started looking into this general problem of file systems and reliability. And so what the outline for this talk is I'll talk about a bunch of related things that we've done in this space. I've divided the talk into 4 parts, and some are very short and some are longer, and I'll give little outlines in each of them. So the first thing that we will answer today is how do disks actually fail, and we've done some work on that. Then the second question, part 2, is really that question that I just asked, is how do systems then react to these certain types of disk failures? And then as we'll see, as the title of my talk may be hinted at, is that they don't always act so well when disks fail and when things go wrong. File systems don't always act so well. And so what we'll try to answer a little bit in part 3 are some of the reasons why this is difficult. What is it about file systems and other storage systems, like RAID systems, for example, that makes failure handling or fault handling difficult? And then part 4, I'll talk about some of the work that we've done in trying to do things in different ways that maybe can address some of these problems more readily. So, make sense? Okay, so let me talk about part 1, how disks fail. Of course, when we started asking this question about how file systems react to disk failure, one of the first things we wanted to learn is, well, how do disks actually fail? Because that's obviously going to influence what the file system needs to be dealing with. What types of disk faults will it see finally when they get all the way up to the file system? And when we started looking around, almost all the information that we had was very anecdotal. So, you could search the web for different kinds of corruption problems, and there'll be some crazy guy somewhere who had a bad motherboard and then went and documented like all the problems that this certain motherboard had. Like there was this one guy that found there was a race condition on this particular motherboard where when a certain disk request would finish right when some other I/O happened, there was a race and you would get data corruption. And there's a lot of stuff like that that's kind of loosely documented. It's out there. We also went and talked to a lot of our friends in industry. So you go and talk, for example, to people at Seagate or other disk vendors. Of course, they would tell you that disks work perfectly, more or less. So I wasn't sure whether to trust them or not. But they also told me some interesting things, like a modern Seagate SCSI drive, for example, has hundreds of thousands of lines of firmware inside of it. That might give you an idea of how reliable disks are. Certainly, it's anybody who has dealt with firmware like that, real-time, low-level code, probably going to be some bugs in there, probably going to lead to some problems. But the disk industry is not a good place to start with if you want to know how these disks actually fail. The good people to talk to are the people who use all these disks, that try to build reliable disk systems, like companies. We went to like EMC, NetApp, other places that built RAID boxes that tried to deal with the fact that sometimes disks corrupt data, sometimes latent sector errors occur, and I'll talk about all these things in more detail. what was clear was that most of the sources agreed that disks failed in interesting ways. They didn't just work or then fail absolutely. There were these kind of interesting partial failures, and we'll talk about them more in a second, but there was little hard data. So we kind of stumbled onto something then. One of our students was interning at NetApp, and it turns out that, and maybe some of you are familiar with this, it turns out that NetApp filers all have this ability inside of them. They basically have a lot of machinery to detect all sorts of disk failures. I'm not going to talk about all that machinery, but lots of checksums and things like that. And it turns out that whenever a failure occurs, they log it in this thing called this auto support database, and that periodically most of the filers, probably not the ones in the government deployments, but most other filers will phone home and send all this data back to NetApp. So sitting at NetApp is this huge database of every disk failure that has occurred in the field over many years. And so we kind of luckily we had a grad student out there as an intern. It happened to be that the chief scientist of the company was interested in publishing more data like this, felt like it was a useful thing to do to get out there this kind of information. And so we kind of stumbled onto this work, really led by our grad student working with NetApp engineers and then later with us as well. And what they studied, and I'm just going to summarize these results instead of going into any real detail. And if you have more questions, feel free to ask them. They studied about 1.5 million disks that had been deployed in many different environments over many thousands of filers. And they looked at about 3 years of data, so it was just a snapshot of 3 years of data. And what they were looking for is, what are the different ways that disks fail? And in particular, we weren't looking so much at, like, when does the whole disk fail? We're looking for cases where, like, a block read fails, or you get a corrupt block back from the disk. That's particularly what we were interested in. Make sense? Yeah? Okay. So let me just give you a very brief summary. And again, we can talk about this more throughout the talk as well. But in 2 different studies, what we studied were what % of the disks exhibited at least one latent sector error, for example. So a latent sector error means, as many of you probably know, when you go to read the disk, let's say you go to read a block or you go to verify a block, like a SCSI verify or something like that, the disk can't give you back the data. So internally, something's happened. The disk can't give you back the data. And what we found, what our student found in particular, was almost 10% of the SATA drives over that 3-year period had at least one latent sector error. And you can see for SCSI drives it was a little bit lower, but they certainly happened there as well. And then we were also interested in, perhaps more interestingly, how often did corruption occur? And you can see for both, again, the SATA drives and the SCSI drives that corruption certainly occurred, though it doesn't occur nearly as often as something like a latent sector error. Yeah?
So by latent sector error, you mean that you read it once, you get a failure, the next time?
It doesn't necessarily mean that. It means that certainly the first thing happened. It might be that if you retry it, that you can get it. We're not able to inject anything, right? So it might be that what happened is the system is trying to read it, and then the disk returned a failure, and it retried and it succeeded. That's possible. It might be that it decided, you know what, I'm not going to use that disk anymore, so I'm going to rebuild it onto some other drive. We don't have control over that. So it just means that at least a problem occurred. Now, of course, the disks internally, as again many of you know, are going to try all sorts of things before reporting a failure back to you. Try aligning things a little bit differently, see if they can pick it up on the next time around, things like that. So presumably in many of these cases, a lot of those things have been tried already before the disk finally gave up and returned to failure. And certainly SCSI drives have some configurability about how many times they'll retry internally before reporting an error. So there's some variability there, and I don't have the data on exactly how these SCSI drives were configured. So kind of bad news. All these things do happen in the field. Yeah. Yeah. So the way I didn't put any slides on this. The way the NetApp filer works, it certainly has. There's a bunch of different schemes they have, but and I'll be talking about this a little bit more later in the talk. But yeah, they have checksums. It's the short answer. They also have some other like identity information and things like that. For example, for a given blocks, they'll record things like, oh, this is supposed to be this offset of this file. So they have some other ways of checking too. But yeah, absolutely, the corruption's all detected. It's only the detected corruption. It might be that there's some other data that somehow the filer doesn't think is corrupt and returned to the user that was corrupt. This is the minimal that the filer detected. Yeah. Good questions. Other questions? Yeah, sorry.
Was there anything specific about some suppliers,
Yeah. Yeah. I think the answer is, your insight is good, is that I can't talk too much about that. And actually, I don't even know, which is probably smart because I tend to talk about things. So the students knew better than to tell me all the actual details of which manufacturers made all the bad drives. But yeah, sure, there were differences. And some of them had kind of unusual behaviors. For example, I mentioned here this bad block number problem. There was one particular manufacturer and a particular drive that they made where, this was very strange, at a particular offset, and only on this drive did this ever occur, almost always that block was corrupt. So you'd write to it, and then you read it back, you'd get back garbage, just at this one particular block. And who knows why that? They looked for, the students looked, and the people at NetApp engineers looked for a long time, is this related to the software? Maybe something was going on in the software. But it showed up only on that one disk. And you can imagine how unhappy you'd be as you laid down like a RAID stripe across that same corrupt block, across all the different drives of the system, and how that doesn't work very well anymore when blocks corrupt in that way. So certainly there were a lot of unusual things across. They were not all identical. If you go look at our paper, there's two papers actually. There's one in Sigmetrics 07 and then one in FAST of 08. Certainly it does break it down by vendor, but it doesn't say who the vendors are. So there's like vendor A, vendor B, and then drive A, drive B, that sort of thing. So there is more data, and if you're a little bit knowledgeable, you can probably figure out, but I didn't say that, except on video, which is now broadcast to the world. You could probably figure it out, but nobody's, I think, gone to the effort of trying to do that yet. Pardon me? Sorry. Yeah. This is over 3 years. Yeah, so it just, I mean, at some level you could say, well, maybe it's not a huge problem. Some of these are just, they exhibited one failure of this type in 3 years. We did see a lot of locality, though. Like once a drive had one of these problems, it was likely to have more of them. It wasn't random. They tend to have some spatial locality, too. So, for example, if something happened on one part of the disk, the errors tended to be near there as opposed to uniformly across the disks. And certainly NetApp particularly takes advantage of some of these things. So when a drive exhibits some number of these latent sector errors, perhaps skewing our data, they'll pull it out of use and they'll put in a new drive and then they'll run some other tests on it before deciding to use it again. So that'll also affect our numbers because the system is actively trying to avoid these failing disks in some way. Yeah. Yeah. That's a really good question. We don't have a ton of... Oh, sorry. The question was, and I'll do that in general. Oh, sorry, I forgot I should do that. The question was, is there a correlation between usage and whether or not, how often corruptions happen? And I don't have a great answer for that. I think it's a great question. It's the data that we had access to, it's hard for us to know. We only have very coarse measures of usage, and we didn't look at that correlation really carefully. It would be interesting to look at that. I totally agree with you. Certainly in a filer like this, there's constantly, of course, the foreground activity going on. There's also constant background activity. There's like nightly scrubs. There's a weekly parity scrub. There's a lot of scrubbing background activity to make sure the disks have data. In fact, a lot of these errors are discovered not by the foreground traffic, but by background traffic, which is going through and trying to make sure everything's accessible. Is there another question up here? No. Okay. So that's all I'm going to talk about that. Again, there's two papers on that, and I could spend the whole hour talking about that, but again, in the interest of time and breadth. I guess I would summarize that by saying, perhaps not surprisingly to people who use disks, that partial failures are a reality. We can't look at a disk as something that's working or failed. We have to think about cases where a block might be, we can't read a block either in a for temporarily or permanently, or a block might become corrupt. That's a reality too, as anybody who deals with file systems certainly knows. And so the way we started to view that is what we call a partial failure model, and we think it's a pretty good way, simple way to think about how disks behave, a modern disk certainly. Okay, other questions about that? Make sense? Yeah. Okay, so the next part of the talk, I'll talk about this part 2, and what's my timing, by the way, here? When do people want to leave? Like they get itchy, they're getting angry at me for keeping on talking? Or has that already happened? But usually 11:30. Okay, that's what I'll shoot for. That sounds fine. And I might go faster towards the end because of course you all have many questions and that's going to slow me down a little bit, which is good. So part 2, how do file systems react to these? So what we were interested in, going back to what I showed you at the beginning, is when we have a file system and for whatever reason one of these errors come up to the file system, a latent sector error or a corruption, what happens? And this is stuff we've been doing over the years. We've looked at a bunch of different systems. And I'll talk about how we do it, but we looked at Linux file systems, we looked a little bit at NTFS, and then we looked at one particular NFS, and we even looked at how like some code that manages a swap partition handles failures of this kind. For interest of time, I'm only going to talk about the first two, and I won't even. I probably should have put a little bit more on the NTFS results, but I didn't quite get there. So we'll talk a little bit about the NTFS. For all of these, what we did is we developed different ways of injecting faults into systems in order to see what happens. So, and I'll talk you exactly, and we call it type-aware fault injection. So I'll show you what that means here. And the real observation, this is pretty basic and obvious. File systems, of course, are comprised of many different types of on-disk structures. And so here's, again, my very simple file system. This is like the original Unix file system almost. A superblock, some inodes, and some data. And of course, each file system has many different on-disk structures, directories, all sorts of things like that. And of course, each file system has different on-disk structures, and maybe 10, 20, 30, depending on the file system. And so all we're doing is we're building a fault injection layer that sits above the disk and knows, oh, this is a read to an inode, or this is a write to a directory, and can fail specifically at a time that we want, can fail a particular read or write like that. That's all we're doing, nothing very clever. And so we're going to inject failures across all those different block types, as illustrated by this dynamic animation. So where we can fail a super block and see what happens when you try to, let's say we corrupt the super block and then we try to mount the file system. What happens? Oh, let's say you're trying to access an inode and you're trying to write to it and that fails. What happens? That's the type of thing that we're doing. It's not rocket science. Like I often say to people, it's computer science. So what we're doing is just trying to see generally what is the policy for these different file systems. How do they react to these different types of failures that we know certainly occur in the field? And so in this part of the study, I'll talk mostly about the Linux file systems that we looked at. And this is, again, a pretty old study, so I'll get more and more modern as this talk goes on. But for some people who've seen this already, my apologies, but I'll go through everything pretty quickly. And so what we'll talk about is Linux ext3, which is a pretty common file system. RiserFS, which for various reasons, strange as they are, isn't used so much anymore, perhaps. And how weird is that? Yeah, well, who knows? I mean, what's really weird is we had interactions with that group, and they were always strange. So it was always a strange group to deal with anyway. But now I always feel bad that our work is related to, a murder. It's just pretty frightening. Usually it doesn't happen in computer science. So some general comment. So anyway, and we looked at JFS. And that's the IBM journaling file system for Linux, actually, the Linux port. And so what we're going to do here, I'm going to show a bunch of results of a bunch of fault injections. And we've, for those of you who've had the misfortune, I guess, of reading some of our papers, you'll see these result matrices like this. And what this is trying to capture is in a kind of concise graphical form how these file system reacts to different types of failures. And so what we're going to show, for example, is let's say you have along the X direction, you're going to have different workloads, and those are going to be labeled in more detail. For example, and these are like little workloads, like recalling a read or a write or opening a file or statting a file, just kind of typical system call, Unix system call type things. And then along the Y direction or the vertical direction, we have the different data structures of the file system, like inodes, data blocks, directory blocks, etc. And so for any particular box, what we're going to try to say is, well, let's say when read was going to do its work, and then let's say it was trying to update the inode with the last time that the file was accessed. So the inode was getting written to, and then what we're going to do is inject a failure there. We're going to say, what if that failed? What if that write to that inode during the read system call, or as a result of the read system call, failed? And what we're going to show there is what the behavior of the file system was. And so, for example, that horizontal line shows, in that case, and this is entirely made up, so this isn't a real result of any kind. But what it shows that the result is that in that case, the file system, when an error occurred, it kind of detected it, and it propagated the error to the user. So something failed, and then maybe you got an error code back when you called that system call. So that would be propagate behavior. What you might also notice is these symbols all kind of work together. And so sometimes you'll see them overlapping. So for example, if the file system, when it detected a failure of some kind, it might have first retried the failure and then propagated it after the retry failed, for example. And so you might see different kinds of combinations like that in these result matrices. And of course, you might see a bunch of gray boxes too like that. That means that particular workload didn't touch that data structure at all. So you can't obviously, whether you inject a failure or not there, doesn't matter because that particular workload isn't touching that data structure. And these are some of the common things you'll see on the next slide. You'll see Propagate and retry, like I already talked about. Stop, which means like the file system did something dramatic, like panic, or for example, some other kind of halting behavior. Like sometimes file systems will, when they detect a problem, remount themselves read-only. That's a Linux thing that's pretty common, and that requires then like a user or administrator to get involved to kind of fix things. So presumably a rare event kind of thing. And then you'll also see this, unfortunately, which is they didn't do anything at all, like they ignored the error, which is surprisingly common. And then this might be, though you don't see much of this, maybe they use some kind of redundancy to recover from the error. So that's the result matrix. Are there questions about that? Does that make sense? Yeah. I think we're not differentiating anything in particular like that. We just took a bunch of Linux file systems, and later we'll do some NTFS stuff. But I guess I don't quite understand. You mean how? Yeah. Yeah, these are all secondary. Yeah, that's true. Yeah. So we wanted to make it so we could boot up again easily. You're right, and you're right. That might be if their system, if the OS at some higher level behaved differently. Because of that, we would miss that. So, but in this case, I'm pretty sure these file systems wouldn't act any differently in that case. And we're certainly, everything that we create, all the files we create and so forth, they're not in use in any way other than just user data and some kind of artificial tree. So we're not seeing how the overall system reacts when it loses critical data. That would be a different and interesting study to do. Okay, so let me show some results. These are kind of hard to look at, so let me walk you through them a little bit. This is on a read. What happens when, like a latent sector, you try to access something and you can't read the data? And let me point your attention up to the ext3 result up there, where you see two kind of behaviors, both a propagate and a stop behavior. So propagate means that the ext3 properly, for a huge number of the errors, detected there was an error and then actually returned an error to the user, whoever was calling the system call. Now, in some cases, we're very generous with propagate. Like propagate means it logged something successfully, and in that way informed the user. So it's a little bit generous of a definition. But you also see that ext3 is very hypersensitive to read errors. When a single latent sector error occurred, it would basically remount the file system read-only. And in other words, that's kind of that stop behavior, that vertical line that you see in a lot of those ext3 boxes. And that was pretty unsatisfying, because it means anytime a transient error occurs in ext3 and you're trying to read something and just like a one-time error occurs, where if you just retried it, it would work, ext3 instead assumes this is a big problem, unmounts the file system, remounts it read-only, and requires really for the system to really continue running, requires somebody to get involved, figure out if there's a problem or not. So kind of an overreaction in some sense if you believe transient errors occur. RiserFS, if I point out this top part here, acted a little bit differently, and it's true certainly throughout its results, in that it would simply propagate the error, but it would keep running. And so it was much better file system in terms of dealing with transient problems. And then certainly what you see across all of these are some of those zeros that I pointed out, cases where a read error was ignored. And what would happen was often bad things would happen. For example, you would assume that a read succeeded, and then you'd use the buffer that you thought you just read some data into and then crash the system or whatnot. And all sorts of bad things happen, obviously, when you ignore errors, as you all are certainly familiar with. So does that make sense, that kind of result? I'm going to show one more result like this. The next result I'll show is for what happens when a write error occurs. And what you can see there, what can you see there? You can see a lot of zeros. That's a bad thing. And the murmuring in the crowd indicates that I successfully explained kind of how to read the graphs, which is good. And what you can see there is a lot of zeros. There are a lot of places in ext3 where write errors were actually just completely ignored. In fact, we started looking at the code, and it'd say things like, I really hope a write error doesn't happen here. We didn't see one in ext3 at that point. Yeah. It has gotten a lot of attention, and actually one of the positive results of this work was we've had very good interactions with the Linux community, except maybe the RiserFS crowd actually, where a lot of things some were simple and they would fix, and they were very good about that. Others were like more what I would call architecturally challenging to fix, if I may say that. Like for example, you'd be really buried way down deep in the code, and dealing with the error at that point was not just a file system issue. It required like some changes in how Linux was managing its buffers and flushing things out. And so it was very challenging to deal with, except, I mean, they could do something like panic the system. That would be one way to deal with it. And in fact, what you see down here is that that's exactly what RiserFS does when there was a write error. It said, I don't know what to do now, but I'm not going to make anything worse, and I'm just going to panic the system. And if these are rare enough, it was fine. Where it really started to bite the ext people was that they started moving from just having locally attached drives to, for example, SANs. And failures, once you put a network between a host and disk, you'll see a lot more problems, not surprisingly. And that's where they really started to see complaints from people about this type of behavior. So some things have been fixed. I don't know, ext4 I don't know enough about yet. We haven't done enough with ext4 yet to say whether it's a generally solved problem. But it certainly was a problem in ext3. And certainly ignoring a write failure that happens at the wrong time can lead to all sorts of bad things, completely corrupt volumes and so forth. So RiserFS, almost perfect. There was one case where there's some code written somewhere, somewhere else off in the code where someone forgot to check for writes, and that was one case where RiserFS didn't do it correctly. So we have a bunch more data like this. I'm not going to talk about it, but I'm going to just summarize a little bit this part of the talk by saying, what we saw was a bunch of different file systems. We actually did a little bit like this for NTFS, so I'm going to go into more detail about an NTFS study in a second. But basically, ext3 was a pretty simple approach, hypersensitive, and then certainly had this problem of ignoring write faults. RiserFS, we call it the Hippocratic file system. If first was do no harm, panic. If there's something that you think you're going to make something worse, just panic. And that was a reasonable policy, actually. It didn't make anything worse. JFS, which I didn't show any results for, JFS was kind of all over the place. Whatever you could think of as an approach to dealing with a failure, it would do sometimes. And I had no idea. It was hard to make sense of it, really, why it would do. Sometimes it was a retry. Sometimes it had some redundancy. Sometimes it had redundancy, but it had a copy of a superblock, but it would never access the other copies, even if the first was corrupt. It was actually pretty interesting. Pretty clearly, someone, long ago there was this, the famous paper out of Berkeley about the FAST file system, which said you should make copies of superblocks because those are important for mounting the file system. So every file system has copies of superblocks, but almost none of them actually use those copies successfully. So there needs to be another paper, and you should use those superblocks. Things you didn't think you need to spell out. One thing that we did notice about NTFS when we were first doing this study, and this is kind of an old comment, is that NTFS at the level that we were doing this kind of fault injection, so we built a file system driver underneath NTFS, is that NTFS was much more willing to retry stuff and try again. And certainly that wasn't, the Linux file systems did that a little bit, but to some extent I think they all presume that there's retries happening at a lower layer. That wasn't true when we looked at NTFS in this study a few years ago. And maybe there's some insight into the room as to why that is. Of course, every time I give one of these talks, somebody comes out of the woodwork and tells me some interesting story. For example, there was a Tandem guy that came up, and he said, yeah, there was a retry policy in Tandem, and it was you always retry 3 times. So every layer, when you want to try something, you always try 3 times, and then the next layer tries 3 times. And of course, you ask somebody why, and then no one has any idea. That's just there was a corporate policy. You try 3 times. And IBM, it was 7. So I don't know what the NTFS magic number is, probably between 3 and 7 because you have a lot of different people working here. So in any case, a slightly more general comment was 2 things we observed. Certainly we observed lots of bugs. So some of these were not design decisions, but bugs. But also we observed something we call an illogical inconsistency. It was hard to make sense of these policies. It was pretty clear it wasn't a first-class concern of somebody to really think about how is the file system going to react to failure at all the different points that I/O occurred. And that certainly seemed interesting to us, that no one had thought about it. Clearly, performance and scalability, lots of other things were first-class file system concerns. Wasn't the case with reliability. It was something that was pretty much an afterthought for most of these file systems. Okay, so that was part 1 of part 2, if you're keeping score. I'm going to briefly talk about some NTFS results in a study that we did. And this is one of those cases where I'm sure that there's much more knowledge. Maybe it's true for the whole talk, but yeah, I'm sure that there's much more knowledge in the room than I personally have. We don't do a ton of stuff with NTFS, that we'd like to do more. And what we were looking at is a slightly different type of fault injection. We were looking particularly at corruption in order to study how NTFS reacted to corruption. And we were doing a particular type of corruption where we would take on-disk pointers, things that were like addresses or indexes into other structures, things that were basically used for addressing in some way. And we would take just one of those and then point it to something else and see what happened. Now that's kind of a mean thing to do, right? And but we want it to be equal opportunity meanies. We were very mean to Linux file systems, so we thought maybe NTFS could get a little bit of a mean behavior too. And so what we're doing for each pointer, just to be specific, is we're going to point it actually to every other type of thing in the file system other than the thing it's supposed to be pointing at. And we're just going to see what happens. Now, you might be sitting there and saying, that doesn't seem realistic. That corruption, when it occurs, probably isn't like one pointer is going to get switched. And I think I agree with that. What this is really about is trying to understand more broadly how the file system is dealing with corruption. And this is kind of one window, one way we can gain insight into that. And again, I probably should have included more on this. Let me just show you the overall graph, which you can marvel at or curse. I'm not sure what the right thing is. And so what we're showing here is a bunch of different on-disk pointers, and then basically what we pointed them to, and then unfortunately sideways, everyone's leaning this way now, is trying to read the key, is what NTFS did when we corrupted that thing to point to a particular thing. And I'm not going to sit here and make you stare at this for an hour, though I will have a quiz at the end. No, what we're going to do here is, and you can see like for example, the black dot is a case where NTFS detected and recovered from the problem that we inserted. You can see the kind of the empty circle over here. Why am I waiting over here? This kind of empty circle was a detection and not a recovery. So it didn't do anything to recover, but it could detect it, which is pretty reasonable. There was some cases like this light gray where NTFS would detect that there was a problem, but then corrupt the file system anyway. And then there was the darker ones like this is there was no detection or recovery. And in some cases, you wouldn't be surprised. Like some things, if you corrupt them, it's very hard to detect that there's a corruption. So like bitmaps are a good example of things like that. And then some cases are that white box, which just means that we didn't do it. It didn't make sense to do that thing. So I'm going to, instead of staring at this thing for too long, though I'd be happy to put it up again if people want to, I'm just going to summarize some of the interesting things that we found. We certainly found that NTFS actually was, compared to the Linux file systems we used, it was used much more thoroughly. It used type checking and like checking of magic numbers and things like that to make sure when it read something that it actually was the right type of thing. So that was good. It certainly had a little bit more replication that it used at the file system level, though it wasn't widely replicating lots of different things. There was some replication that was used, but there were certainly some interesting things that happened that probably weren't quite intentional. Certainly there were some cases, I don't remember which structure this was, you all would probably appreciate this more than I do, but there was a case where there was something that was replicated, but there was only one pointer to it. So, and then the other thing, the replica was at a fixed offset from where the primary was. Maybe it was one of the security things, does that sound right? Yeah. And so when you corrupt the pointer, well, it doesn't matter that you have two copies when you corrupt the pointer to that thing. That's, it's a silly thing, but it's kind of interesting. And then there were cases where the replicas weren't exactly treated as pairs. There was a case where we would corrupt one block. I should have written down which exact pointers these were. We would corrupt a particular block, and NTFS would detect that it was corrupted, and then it would propagate that corruption to the other copy. So it really trusted that block, which was interesting, when it had a perfectly good other version. So what? Yeah, no, it's all in the paper. I should have put more slides down for this part of the talk, and we can certainly go through them in the afternoon if you'd like to. Yeah, so this is certainly a harder study for us to do because with the Linux ones we could always make sure that we were right when we would go look at the source code and say what happened, and here we didn't have that, and to some extent, whether or not we had the source code, what made our lives easier in the Linux world was that it was very easy for us to fire off a mail to the developer, and we'd get responses back, and they were usually civil. So if doing more NTFS work, what I would really love, if people are interested in it, is figuring out who such mails would go to, so we could get back the same kind of response that we found in the open source community. So just a random comment. Okay, so that's part 2. Now I'm going to go through part 3. I'll talk about some of the reasons fault handling is challenging. This is probably more Linux focused, though we also look at some commercial file systems. I'll briefly talk about some work we've done in looking at Linux file systems and automating some little static analyses we've done, looking at why these problems occur. And then a lot of the response I would get from industry when I would give this talk, like I go to a storage vendor, for example, and give this talk, is like, yeah, okay, Linux file systems, everybody knows that those stink. So no big surprise. What you should really look at are some of these really heavy-duty commercial systems like a NetApp filer or EMC, a RAID system, which has a ton of machinery in it to deal with these types of failures. And everybody guaranteed that we would find many fewer problems there. And to some extent that's true, but we found some issues too, which I'll talk about in the second part of this. Oh, this is part 3. That's wrong, part 2 outline. Okay, so this is part 3. So anyway, let me just show you a little snippet of code here. This is something to sync some data to the disk, a routine in the Linux FS code sync block device. You can see in this code, there's a couple underlying routines called file map data write and then wait. So write some stuff, wait for it, and then return some kind of error when you're all done, if there is one or not. And you can see this is a very common pattern in the Linux code where this routine would be called like that. So whether or not there was an error being passed back, it was just called like that. It's the simplest thing in the world, which you would assume that any programmer wouldn't do. Surprisingly, this was found all over the place in Linux. And so we figured, and there were other cases that were a little more sophisticated. Like, for example, someone actually got the error code back, but then they'd lose track of it, or they'd overwrite it by accident with something else. But in any case, plenty of cases like this. So we thought it would be nice to study the Linux file systems without having to look through each one by hand. And so one of our students basically built a tool to do that. So, and I'm not going to talk about the details of the tool, though other people have used it, in fact. So if anybody's interested in using it, we'd certainly be willing to help. But basically, you start with the code, looks at this tool looks at the source code, starts with like the basic error codes that can be generated at the low level of the file system, like from the disk, like an EIO, for example, is a very common general error that occurs in Linux world. And then just does a little analysis to find what happens to this little integer error code as it makes its way through the gory file system. Does it, for example, get handled by anybody, or does it get lost like we saw in that example? And handled here is very generous. Like, handling an error means someone wrote, if this error, do something. Now, that might not be a good way to handle an error. Like, for example, if this error, print, I don't know how to handle this error. We would call that handling the error. So we're being very generous here in terms of what handled means. And then what this tool would return is where are all the places where these error channels got broken. In other words, where an error got lost or overwritten. And what I'm going to show you are these kind of semi-complex graphs of source code and all the functions and all the places, all the other routines that they call. And then when you see these orange ones, you know that that's something bad happened in here. Like, it called into something, like over here, and then ignored the error code. And that's what that heavier line means. Of course, you can't read what all the function names are, but you can get a sense by looking at, for example, ext3. There's plenty of places throughout the code where errors are simply lost or overwritten. That was the reality at that time that we did this study a few years ago. One thing that's interesting, and I'll show you a few more results to give you a flavor, is as this talk was going on, there were Linux developers in the audience, and they started fixing bugs during the talk, which is, I think, our fastest impact from our research. But also, they confirmed a lot of many of the bugs by hand. So certainly these are real bugs that are found. Some were easy to fix, and some they're still thinking about. This is RiserFS. That one's kind of interesting. That one was a little bit better in handling errors, and you can see it's a different structure than ext3, and certainly it probably has fewer errors. And then probably the most interesting one was SGI's XFS, which is a very complex file system, as you can tell. Doesn't that make sense? What's funny is I later met an XFS developer, and he said to me, "Oh, XFS, that was so much fun." He's like, "Anytime we could do anything to improve performance, even if it was wildly complex, we did it." And I said, "Yeah, I know that already. I've seen it." And you can see also it has errors scattered throughout. And you can see certainly how many layers it takes to go from the top all the way to actually issuing a disk I/O. It's no surprise that errors get lost in there. Certainly it looks like quite a jungle to navigate for a poor little error code like EIO. In any case. So that's just a quick summary of that. We looked at actually 50 Linux file systems. There's actually 50 things called a file system under the Linux source tree, though most of them aren't real disk file systems. We looked at 3 drivers, too, to see how drivers propagated errors. And we found overall in Linux, about 1 in 10 calls dropped an error that should have been passed on to somebody or done something with. And why that is, it's kind of ridiculous at some level. There were a couple file systems that didn't drop any, but most dropped some. And certainly, I think some of those interfaces aren't super stable in there, too. So things will change over time, and then the code won't migrate to deal with the new way errors are being passed. Error handling, error passing always seem to be a secondary concern. So that's that tool. Let me go through, this is actually the part 3 outline. I did that incorrectly. Let me go through some work we did with commercial RAID systems. I'll do this part pretty quickly. as we've talked about already, there's many different causes of corruption. I haven't really talked about why that is. Sometimes there's some kind of bit rot, whatever that is, something happening on the disk, some bits get flipped. But there's also all sorts of interesting areas which really relate more to the fact of the complexity of writing something to the disk, the complexity of a controller, for example. I already alluded to the fact that like a Seagate disk has many hundreds of thousands of lines of firmware. A RAID system on top of that, hundreds of thousands of millions of lines of code. All these things, if they have bugs, can lead to funny problems happening. For example, lost write is a common problem that some of you may be familiar with. When you told the disk to write something, and it said, yeah, I wrote that, and then you go to read it, and it's like, I didn't write, you never wrote that. Yeah, sorry. And you get back the wrong data. Who knows why? A misdirected write, where you write to, you say you thought you wrote the block here, the disk said, yeah, I did that, but then it actually went somewhere else on the disk. You can imagine that's problematic both from where you wanted the data to be, and then for whatever poor data you overwrote during that misdirected write. A torn write. Some files, if you're not careful, you start thinking of disks as being atomic as a 4K thing that you're writing, but really disks are really guaranteeing that 512 byte write is atomic. So sometimes when you write out 4K, only part of that 4K gets written out, let's say. So we call that a torn write, and then what happens when a torn write occurs? And so we started to look at that, and where we started to look at that was in the context of RAID designs. So what I'm showing here along this direction here, a vertical direction, a bunch of different RAIDs or other kind of reliable systems. This is like an Adaptec RAID card, Linux software RAID. This is just an old operating system that did some reliability things. This is an old tandem design. And these are more modern RAID systems, including ZFS. And what I'm showing along this direction right here, this X direction, are some different techniques that these systems use to detect and recover from corruption. So they all these systems except one that we're looking at are using kind of parity-based RAID schemes. I'll assume everybody's familiar with. Many of them use scrubbing, so they'll go through the disk periodically, read in everything, and then see if they can read everything correctly, and if so, maybe recompute the parity, make sure the parity matches up. Some of them, and then all of them use different types of checksums. There's a sector checksum, so for every, let's say, 512 bytes, you might add an extra 8 bytes, like some SCSI disks support that. Behavior, you can add extra 8 bytes, which is just a checksum over that sector. You can have a checksum over the entire block that you store, so for every 4K. You can have, ZFS uses what we call the parental checksum, so it's an inode, for example, that's pointing to a data block, it'll store a checksum of the thing that's pointed to. Some of these systems do a write verify, so you can configure them to, after they write something, to read it back and make sure it actually got to the disk. Which is obviously bad for performance, but might be good from a reliability standpoint. And then some of them add some different kinds of identification information into their checksums. Like a physical identification will say, oh, this is, not only is this block here and it has a checksum, but this is, offset 12 of disk 6. So it's a very physical way of saying, when you read it back, sometimes a checksum can match, but you can imagine if you wrote it to the wrong location, the checksum matches if you don't know what block it's supposed to be. So some of the systems have that kind of protection in them as well. And what you might get when you look at this, and this is certainly what happened to us, is, wow, there's a lot of different things that people are doing. And given how modern disks fail, which of these makes sense? Which of these things work? And it wasn't obvious to us, which was the best approach, for example, just staring at it. And so what we did to deal with that is we built a little what we'd call a RAID maybe design checker, which would basically take as input a RAID design like this, like, oh, I'm using this type of checksum, and I'm using this type of scrubbing. And it would take input as the types of faults that occur, like the different corruptions that I talked about a moment ago. And then basically what it would do is just model a single failure happening at different points in time. So like, let's say I wrote something to the disk, and then a corruption occurred, and then the system came through and scrubbed the data, and then somebody tried to read the data. Or different things like that. And it would basically go through all the different permutations that it could, and output either a flaw in the design, oh, here's a place where a corruption occurred, or a proof that it couldn't find any such flaw. And so let me walk you through one example of that. It's a problem called a parity pollution problem, which we actually observed as a very general problem in parity-based RAIDs. And what I'm doing here in the vertical direction is I'm going to show the changing state of the two stripes of a RAID system. You can see there's 3 data blocks in a parity that is, just the XOR over all those 3 pieces of data in a stripe, and there's 2 stripes. And this particular RAID, let's say it has parity protection, and let's say each block has a checksum, and then let's say it does write verification. So after it writes something to the disk, it's going to read it back and make sure it got back the right thing, the correct thing. And so we're going to show first nothing's happening. Then let's say we're trying to write to data block 1 in that first row, but let's say that got misdirected. Let's say it instead, it wrote when we're doing a small write in RAID, we're going to read data block 1, we're going to read parity block 0, we're going to compute the change in parity, we're going to write out data block 1 and write out parity 0. I probably could have animated that better. But let's say that write to data block 1 got misdirected and went to data block 5, where data block 5 is. So it should have written D1 prime to where data block 1 is, but somehow it wrote it to a different disk at a different offset. Then the system says, well, I'm going to do a write verify. So I'm going to read D1 back and see that it's not D1 prime. And so I'm going to write it out again, and that works. And to some extent, that system's kind of happy then, because it said, well, now I know that at least that thing that I was trying to write, I wrote it out. But it doesn't really know about that misdirected write, the fact that D1 prime overwrote D5. And now, of course, if anybody reads D5 at that point, it just has a block checksum, so it doesn't have any identity information. You're going to read it back, and it's going to look fine. So that's a problem in this type of protection scheme. And even worse, what will happen in these systems is that sometimes the scrubbing will go through. It'll read all the data blocks in and compute a new parity block and write that parity block out, because clearly the parity doesn't match the existing data blocks. And so what we call that general problem parity pollution, when like something is bad with the system, but it's recoverable because we only have one bad block at that point. We have parity, we have two data blocks. We could have recovered that if we knew it was a problem. Instead, the system comes through, reads all the data, trusts it, and then pollutes the parity with that bad data. And now it looks very reliably. It's stored in the data. And we found this problem in almost every design that we looked at had this type of problem. And in fact, after we did this work, there was a number of people who got in touch with us, and some of these systems that we looked at have been fixed as a result of that, and to add a little bit more protection to not have this parity pollution problem. So just a hint of what that is. And I'm getting towards the end of my talk, so I'll go through this part quickly. All the designs we looked at, RAID designs, had problems. Dealing with corruption is very tricky. Depending on how the corruption occurs, you have to do different types of things, and you have to be very careful thinking about how are you dealing with all the different cases where just a single corruption could occur. And saying that your system is foolproof to that, I think, is a very hard thing, or at least harder than just dealing with the fact that a disk failed, for example. Okay, so this is the last part. I'll go through this pretty quickly, just give you a sense of a couple things that we did. And I'm not going to talk about all three of these. I'll talk briefly about two of them. And I think since I have 5 minutes, I'll probably not even do that. But I'll talk about these two, and I'll skip that last piece anyway. Our general thing that we've been trying to think about is, how can we do better than this? How can we do better than the state of the art, which seems to be, for most things, it's writing a lot of C code is how we build a system. Maybe it's C++, but that's not a big difference in terms of what that means. When you write hundreds of thousands of lines, tens of thousands of lines of code, it's going to have these types of bugs in it. You can be better about it. You can certainly be more careful about it. But it's very hard to get these things right. And so we were trying to think about how to do things that are a little bit different in terms of dealing with failures. This first thing that we looked at is can we redo a file system checker? So the idea, of course, of any file system checker like FSCK is a classic Unix one, is to turn a corrupt image into a consistent one. That's, of course, very easy to do. You just return an empty file system. So there's clearly some other requirements that I'm not mentioning. But certainly, virtually all file systems have these. FSCK is one of these interesting things. Every time there's some new file system group that comes along, they're convinced they don't have to write a checker. So XFS came out from SGI, and they're like, well, you'll never need to check this file system ever. And then what happens is some customer calls says, we have a corrupt image, and we need a checker. And then you determine how much they've paid you, and then you write a checker. NetApp had the same thing. They've shipped, they say, we don't need to check this ever. Sure enough, there's a checker. Now, most lately, Sun ZFS came out. If you look at all the marketing literature, you never have to check it. I would be willing to bet money, well, if Sun continues to exist and support ZFS, or if ZFS continues to exist, because clearly Sun isn't at some level, that there will be a checker, because eventually somebody important runs into an image that somehow got corrupt. Why does that happen? Well, gee, you wrote 100,000 lines of file system code. Does it ever make a mistake and write something that looks like it passes checksum protection? Yes, of course it does. So anyway, we were looking at FSCK and wondering, are there different ways to write this than just write 20,000 lines of C code or 30,000 lines of C code? And so that's what we did. I guess let me describe the state of the art. I guess I did that a little bit. How do you build FSCK today? You write a lot of C code or whatever, C++, some variant of C. Then you do a lot of testing. And then you tell customers to take frequent backups. So that's the state of the art. And the state of the art.
Backups are valid.
Well, right. You know what's interesting about that? I think a lot of times they're valid because someone else wrote it. It's like N-version programming, right? Somebody else did that. So the odds of you making the same mistakes are lowered. And it's kind of unintentional. I don't think people thought about this, like, oh, this is why we should do this. But the reality is backups are usually done by tools, right? And that may be true in your world. So I think you're right, though, that if you read the bad data, you're going to get bad data, and you have a problem. So I've been thinking about that. So anyway, here's an example of a problem we found with the current E2FS, the ext2 checker, which has been used for many, many years. The problem was, well, anytime you have a bad pointer in this checker, like a pointer that points, for example, outside of the disk, it just clears the pointer. Now, that's not a great behavior, but it leads to a consistent image that kind of makes some sense. So it doesn't, for example, lead to you trying to read something that's outside of the disk. Now, the problem was when we changed like the indirect pointer in an inode. So the indirect pointer points to a block, which is full of direct pointers to blocks. And let's say we corrupted that one to point to something else. It turns out the ext2 checker would clear the pointers in the pointed to thing before checking whether the indirect pointer itself made any sense at all. So for example, if we took that indirect pointer and for whatever reason we corrupted it to point at the superblock, the E2FS checker would simply go through and clear out the superblock. And then it would say, you know what, this checking didn't go as well as I thought it did. It's supposed to. And in fact, it would yell at you. It would say, you must have done something stupid, like run this on a mounted file system, you dummy. It would like yell at you because of their bug, which I thought was most interesting. I've never been like insulted by a checker before, but this one has some insults built in. Maybe that's a study of future research. So anyway, really quickly, I'll tell you about what Squeak is, which is a declarative checker that we built, where the idea was, you know what, the things that you're trying to do in checking are very high level. You're trying to say, here's some properties that you're looking for. Like, for example, for a data block, that no two pointers point to the same data block. That's a very easy to express property. But we're expressing it right now as tens of thousands of lines of C code. So instead what we do is we basically load all the metadata of the file system into a database, and then we just run queries over the database. And that's how we do checking. And I'm not going to get into the details because I'm out of time. But if you want to talk more about it, this is what pieces of these 100 or 200 queries look like. These are simple things that make sure, like, how many people are familiar with SQL, for example? Many. So you get this is like a pretty simple looking thing, looking for a bad pointer that looks outside the group. This is looking for those illegal indirect blocks like that example I showed. It's just simple SQL. It just looks kind of straightforward. And I'm not going to go through the details. Here's one that's even a little bit complex, certainly hard to do inside of the current checker, which basically checks that parent and child directories agree. Like the parent says, that's my child, and the child actually says, yes, that's my parent. In the standard checker, this type of check was very hard to do and sometimes done incorrectly. But in Squeak, it's very easy. So anyway, the bottom line here is we turn thousands of lines of code into hundreds of lines of SQL and certainly hundreds of queries, which are much easier to understand, I think. So that's one way to address this kind of complexity. I'll just briefly give, if you have one more minute, I'll give you an idea of one other thing we did. Other thing that you could say is clearly file system bugs are here to stay. If we're going to keep writing file systems like this, that's just reality. So we tried to embrace, in this little piece of work, we tried to embrace that reality, that we're going to have imperfect file systems. So what can we do about it? And so the idea here was to use N-versioning. This is not really practical, but it was kind of fun to do. Instead of using one file system, we're going to use 3. And we're going to store all our data in each of those file systems. So we're going to take every read, or every time you create a file, it's going to be created in 3 different file systems. Now the problem with that is it's really slow and it takes up a lot of disk space. So we added another layer, which then coalesces those same blocks back into a single copy underneath. So the neat thing about this is it's still possible to detect a whole bunch of file system mistakes without using all this time and space overhead that making 3 copies of everything would. And of course, the real benefit of this is that there are already so many Linux file systems out there, we don't have to do all the hard work of developing a bunch of different independent file systems. We can just use them off the shelf. So there are a lot of issues in doing that. I'm not going to talk about them, but let me just describe one example of how we can coalesce space using a single instance store underneath all this and still detect certain kinds of problems. So let's say you're writing some data to this thing. You write it to this thing called NTFS. I'm going to show this because I spent some time on this animation, so my apologies. So it's going to write it all to the different file systems, and then let's say this one of these file systems corrupted the data before it wrote it out. So that's kind of a really hard case for a file system to deal with today. It corrupts it before it even, let's say, computed a checksum over it. So it's going to go to the disk corrupt no matter what. What the single instance store layer do is it's going to coalesce the 2 that are the same. That third one is going to get written out differently. And on the disk, they're going to sit like that. But when we read them back, 2 of the file systems are going to get that orange block. The child one that corrupted is going to get the corrupt one. And then NVFS is going to vote, and it's going to give you the right data. So you can still do this kind of coalescing and get some back of the time and space overheads, but you can have the reliability that all 3, 2 of the file systems had to have made a mistake for you to get some corrupt data here. Now, again, there's much more detail there. It just gives you a hint of the type of things we do. I don't think this is particularly realistic or something that's really deployable. Actually, probably the most interesting place where we've used it is for debugging. We found that there were some bugs that we uncovered when we did this because we'd immediately see when file systems would give us back some different result. And then we uncovered this Linux bug that had been in Linux for 2 years because it would happen during an operation, but it would only manifest at unmount much later. But in our thing, we would check right away, and we'd see the problem right away. So I think this might be useful in a debugging environment, even across different versions of the same file system. So anyway, I'm not going to go through this part. And I'm going to conclude, which is good, because I promised I would. In this talk, hopefully, I've talked a little bit about how research begins. For us, it really begins in the small. We noticed something strange about how file systems behaved in terms of reliability, and that led to really 4 or 5 years of work. We found a bunch of problems that it was really the whole approach to reliability in most of the systems we looked at was pretty ad hoc. And I think that the underlying cause is really how we build things. We're just so used to building things by saying, okay, now go off and write 100,000 lines of code to build this system. And it's just fundamentally, I think, going to have problems in terms of what types of behavior we should expect from those systems. That's a complex system. It's going to have complex problems. And I'll give you a couple examples how we might deal with that, though there's clearly much more work to be done. I should give credit where credit is due. Like Galen said when he introduced me, all of this work is co-advised with my wife, Andrea, who we've worked together at Wisconsin for 10 years, and a little bit with a couple other professors, Mike Swift and Ben Liblet. And of course, here's my last animation. That's not very exciting. It's the people that did all the real work are students over the years, many who've graduated, some who are still around. And I would say the core 3 students that did most of the work, a lot of the work that I discussed in this talk were Lakshmi Sundaram, now at NetApp, Haryati, now headed for a postdoc at Berkeley, and then Vijayan Prabhakaran, who's at Silicon Valley. All great, of course, all of them great students, but those 3 did a lot of the work that I talked about today, and I'm happy to try to take as much credit for as possible. So, in conclusion, if you want to learn more, you should. Oh, I'm sorry. You should look up I told you I pander to the audience. So you should, of course, look up my name, and that's probably the best way to find anything more. Yeah, actually. I bet I am. I don't know. Someone try it. I think that I didn't even test it. That shows what a good programmer I am. Yeah, thank you. So if people have other questions, I'd be happy to take them, and otherwise do we have time, or should we, or if people want to leave, that's okay too. Yeah, so feel free to leave, or ask a question, or sit there awkwardly wishing you had left, while someone asked a question you didn't want to hear the answer to. Yeah. Yeah. Yep. Yeah. Yep. No, that's a good question. Yeah. So, yeah, I mean, I could have put up some more. So, oh yeah, sorry. So the question is basically about the performance of using the SQL-based approach to building something like a check disk or FSCK, and is that what are our performance claims, I guess, and then what are the differences? Yeah. Yeah. Yep. Yeah. So what we did was, and when I say we, I mean poor grad students, was look at every check that's done by FSCK, the Linux ext2 checker, and took all the ones that were interesting at all, like ones that weren't just so simple, like, oh, check if this field of this inode is, some reasonable time value. Some of those we didn't do because of just time constraints. We took anything that was interesting. There's about 120 interesting checks, and we re-implemented all of them. So I think it's totally believable that we do everything that they do, and there's some ordering to those actually that I didn't talk about that you have to get right. which is a little bit beyond just you don't just do queries in any order. You have to think about what order to fix things. And we just followed the ext2 and general FSCK approach to the ordering. What I would also say is was very easy for us to add more checks because it's, once you have the database there and you can just write queries, you could do more. And it was easy to add them as opposed to like no one would touch that, ext2 checker because it's just complex and people were worried about making mistakes with it. Here it was easy to add new things. And so we did a few new checks too. From a performance standpoint, performance was okay, I would say. We were going for the common case where on a pretty big file system, like we tested on a terabyte file system that was about half full. Some people in the room tell us that file systems are always half full, so we thought that was a good way to test. And when we were running our checker versus the standard ext2 one, which has been tuned over the years, we were probably within a factor of 1.5 without too much effort. It was a little slower in general, but I think that wasn't fundamental to it. So I feel very confident that we could do any check they do and more easily. Performance, I think, it depends a lot on certain things. It ends up becoming a database performance tuning issue, how do you put data into the tables? And that's stuff that I guess because we're not database people, we don't find super interesting. So we did the minimal that we could so we could say the performance was okay. Yeah?
So at least some percentage of our problem is that we file system people are slackers and we drop 10% of our errors on the floor. Is that a good or bad number? Have you looked at sort of other bodies of code? Does the rest of the world drop 11% of their errors? Or?
Yeah, no, that's a good question. So the question's about is 10% of dropping 10% of errors good, bad? Does it matter? And maybe do other code bases other than Linux have similar problems? We haven't really done a thorough analysis. I think that when we've gotten access to some code bases like, for example, NetApp, we've done a little bit of taking this type of tool and trying to apply it inside of NetApp on their filers. And it's pretty clear there's a different standard of software engineering. And I suspect it's true with your guys' stuff too, that people are a little more careful about really silly errors like that happening. Now, almost every system we look at still has problems because it's just hard to, sometimes it's very easy to misinterpret what an error code means and things. I think that's a harder problem, and I think that, that's not, even if you're careful, you're not going to necessarily avoid problems like that. Certainly even some Linux file systems were much better about dropping errors. And I don't know, your other question is, what's the right number? And that's a really good question. I have no idea. What is it, do these problems manifest in practice? That's kind of what it relates to, right? Does the fact that I ignored an error here, is that a problem? And to the extent that we looked at it, we certainly went back and injected faults that would cause these problems, and they would cause problems, but I have no idea how often they happen in the field. And that's a very interesting question that I'm not able to answer right now. Yeah. Me too. Yeah. Yeah, sure.
It looks like you're trying to take a file system that has some corruption on it, or that is going to become corrupt because the file system has bugs in it, and then be able to detect and repair those consistency problems. But is there any, like one thing you said is lists are bad and they don't go bad completely, and you'll have to live with maybe, I don't know, whether it's a bad splatter or a bug in the firmware that
Yep.
the line of blocks is always
Yep.
at some point or
Yep.
whatever.
Yep.
Do you have any work or any
Yeah.
plans on how to address those things in a way that lets you
Yep.
continue to use the drive beyond just, you write this block is always bad, we'll always do something bad, and
Yep. Yep.
we'll always be able to pick
Yep.
up redundancy correctly and recover it.
Yep. No, I think that's a good comment. A lot of what we were trying to do is, and there's one piece of work that I didn't get a chance to talk about. I think the problem exists at many levels. There's one problem, which is there are bugs, and that's a reality. And so it's an interesting question of, given that reality, how do you still think about building reliable file service? And what does that mean? Now, there's another problem, which is sometimes disks have faults. And then it turns out that bugs often relate to those kind of uncommon cases of like when the disk finally has a problem, then you'll see bugs in your code, right? Because that's the code that's not exercised as much. So one thing we've been thinking about along those lines are, for example, how do you write a file system so that those cases aren't as exceptional? So that, for example, you commonly deal with whatever types of problems occur, so that you know that that code is really tested and beaten up. Certainly another thing that we were thinking about, I think another problem that we saw, was that these file systems, like I kind of hinted at earlier, reliability was a second-class concern. It wasn't from day one, how are we going to deal with disk failures? Even if you have RAID systems and a lot of checksums and stuff like that, it's possible that you're going to get something unexpected back from your disk layer, whatever that layer is. And so I think it's interesting to think about how should file systems be a little bit more defensive in terms of what they're getting back. And one thing that we did that I didn't talk about was we built this layer underneath of Linux file systems that was meant to basically do all the types of reliability things that a file system wants to do. And that way, when we get anything back from the disk, we would immediately act on it in a very consistent and uniform way. So that was another way to address that kind of problem. So I think there's a bunch of things there that one can do to improve the state of the art. You're right, though, at some point, though, if the disk is bad and it's repeatedly bad, there's not much you can do about it. You need other disks then, or you need to stop using the disk or whatever. But certainly there's no reason for file systems to do silly things like ignore the fact that errors occurred. Or even, when they get back a structure, they should be able to do some kind of checking. Does this look like what I expect it to be before I start writing blocks all over the disk or all over memory or whatever as a result of that bad block? So I think we're just trying to, really at a high level, what we're trying to do is raise awareness of this problem. I think in the Linux community, we've actually done a pretty good job. And certainly they were aware of these issues too, so I don't mean to take any credit there where credit isn't due. But that's kind of, really I think our goal is to get people to think about this when they build file systems and the different types of things they can do. There was another question? No? Yeah. Yeah. I think it was XP Service Pack 2 or something like that. Yeah. No, that would be interesting to look at that. And then that's just an issue of human power. And the funny thing about the academic community, as a lot of you know, is there's very little reward to doing the same study again. There's not, for some reason. So our academic reward for that, I have a personal interest in that because I think it's interesting, but it's hard to convince a student to do it because it's like, hey, didn't we just do that? But I think it would be interesting, and I'm trying to figure out other ways to do that sort of thing on a more regular basis. Oh, thanks.